Artem Danilov from Attocube company and the Neaspec team and department there. And he will be talking about the applications of scattering, scanning, near-field optical microscopy, and spectroscopy. Artem, please.
Yeah, thanks a lot. Can everybody hear me? Yeah. Okay, good. Just to confirm. So yes, good morning, everybody. I'm here today in ITMO. I'm very proud to be here to have a talk in an optical seminar. Today I had a long flight from Novosibirsk and just arrived here. So yeah, today I'm going to talk about the scattering type of scanning near-field optical microscopy. So maybe a few words about myself. Yeah, my name is Artem. I'm working in a company which is called Attocube Systems AG, which is a company producing nanoscale motion sensors, piezo stages. And my department is called Neaspec. Neaspec used to be a company and now is a department of Attocube, which is producing atomic force microscopy in combination with optics. Can I move on? Right. Okay, no problem. I'll just quickly go to the outline of my presentation to tell what we will be talking about today. So I'm going to introduce briefly basically the company and the background of what I'm going to talk today. I will tell more in details because here all of you probably experts in near-field optics more or less, or metamaterials. So I will concentrate a little bit on the technical aspects of the technology which we're doing. And then I will move on to applications in some scientific areas where we implement our technology or where our users are implementing this technology. So basically, this is the overview of our users, what our users have done with this. And then I also had a few words about quite interesting combinations or developments which can be done also with this instrument. So let's make this in the format of seminar more or less. Yeah, whenever you have questions, just probably go straight ahead. Not too much because my presentation is quite big, but in the end I can skip something which is not that relevant. So moving on, the first part, introduction, is basically regarding the company. The company was founded as a spin-off from Max Planck Institute of Biochemistry in Martin Street in Munich about 15 years ago. Starting by Rainer Hillebrand, Neonato Schelic, and Fritz Kallmann, basically near-field optical microscopy pioneers. Now our team has grown to roughly 40 people for these 15 years of existence. We have sold about 200 systems around the world. And recently we've joined the Attocube Systems company, which is producing high vacuum AFM devices integrated with optics as well. Moving on to the topic itself. Today I'm going to talk about the optical or infrared spectroscopy as well and why it is so powerful. We can see it on an image on the right side, but there's a lot of things which can be investigated by optical microscopy at different energies, and we can make a chemical characterization of the material. We can search for some structural properties, conductivity maybe. So in general, optical microscopy and specifically IR microscopy or spectroscopy is a very powerful tool. The problem with this type of measurement of this approach is the resolution of it is limited by diffraction law, which is roughly half of the wavelength of the light. And for IR spectral ranges, it's about 5 to 10 microns, which is quite big. We have another type of optical spectroscopy, which is Raman spectroscopy, which is better in this regard because it uses a visible light, but it's really complementary to IR spectroscopy because due to restriction laws of transition laws, some peaks which are visible in IR are not visible in Raman, and the other way around basically. So we really need to use both techniques, and it's really important to have a good resolution for IR spectroscopy. And here's the main point basically of what we've done. We decided to make a combination between the conventional FTIR microscopy and the atomic force microscopy, just to get both the nanoscale optical resolution, and optical chemical identification of material. So I will move forward to describe this more in details. This is how our system is working, basically, and this is the setup inside of it. You can see basically asymmetrical Michelson interferometer. The technique which we are basically using is called scattering type of scanning near-field optical microscopy, or simply s-SNOM setup. Typically, yeah, there are a lot of varieties of s-SNOM. I will move on to show a few. In a simple words, yeah, if you would try to describe what is it exactly, we have a tip, atomic force microscopy cantilever, which is oscillating on a sample. We have a light which is coming to the tip, which is exactly fine-tuned to illuminate the apex of the tip. Then, in the process of tip oscillation, we create basically a ultra small nanofocus, as some can call it, but essentially this is some physical phenomena related to near-field optics. And then out of this nanofocus, we're basically collecting our light back to the detector. And what it gives us is essentially wavelength independent 10 to 20 nanometers optical resolution, which is governed by the diameter of the apex of the tip. And this is suitable for visible, IR, and even terahertz ranges. To go more into details, there's a theory explanation what's happening basically there. So suppose there is a tip. The tip is essentially is a metallic conducting nano-antenna. By illuminating it with the light, with the polarization, which is more or less directed vertically to the sample, we can create some collective oscillations of charge carriers inside this nano antenna, thus creating the dipole. And it is considered that this dipole is creating the image dipole in the matter itself. And then the other way around as well, this image dipole on its turn is creating the response in the tip, and the tip is changing its optical properties, and that's something which we can sense with our equipment more or less. So if we go a little bit to the math, we can see that there is a scattering cross-section of the tip, and it's somehow connected to dielectrical permittivity of matter. So essentially, this principle is could be used for making spectroscopy at nano level. To go a little bit further into details, how SNOM setup is working and how we extract basically the near field. So we have our SNOM setup. We have a cantilever which is oscillating at a certain frequency. We know that there is a far field which is typically propagating in a vacuum or in the air in environments. And this far field is obeying the dispersion law for the vacuum, basically, that you have a proportional spatial frequency and frequency of oscillation, and the proportional coefficient is the speed of light in the matter. So what is happening if the tip is oscillating at specific frequency and is changing varying its height, is that far field is moving more or less linearly, whereas there is a near field which is coming from a sample, and near field is really bound to a sample. So the light can travel as a far field only if the dispersion law is correct, but there are some other waves which are propagating in matter which cannot leave the matter because the dispersion is not allowing to do so. So the principle which we're using here is demodulation at high harmonic. Demodulation means that we're extracting, basically we can vary the distance, and we can see, put our response into Fourier series. And if we carefully analyze it, basically, because far field is linear, we would just get some linear response. Whereas if we're talking about near field, because it's exponential, it's an evanescent wave essentially, we would see a response which in spectra would occupy high harmonics, more or less. And that's what we're doing, or that's how SNOM is basically working. We're demodulating at higher order harmonics to get only the near field and not getting the far field into our detector. So, sure.
In your system, are you using just one harmonic, or do you sum up several harmonics?
I can talk about later how exactly we implemented it, but essentially a classical SNOM implementation or scattering time implementation is to demodulate at higher order of harmonic. The higher you go, like if you go for third or fourth one, that basically you have more of a near field part in it and less of a far field in it. But on the other hand, you're also decreasing the signal. So signal to noise range is going down. Typically, if you're working in IR range, it is accepted by community where you should stick to optical harmonic of 2, more or less, or for visible it could be 3 and 4, but that's the details. Okay. The classical setup for SNOM is called non-interferometric detection or self-homodyne detection. Essentially, you eliminate the tip apex with focused light, and then this light is coming to detector, and then we demodulate at higher harmonics, and what we're getting is basically a near field amplitude. However, this method is not sensible to phase information because we're not using interferometer, so why couldn't we use it? There's a second setup which is called interferometric detection or homodyne detection, also known, where we can put a beam splitter in front of the incoming light and split our beam to 2 parts, where one is coming to reference mirror, and the second one is coming to the tip. And then we combine these pulses or these lights together through a beam splitter again, and then we can detect as well the near field amplitude and the phase. So this method is both amplitude and phase result. However, if we check carefully what's happening exactly, the detector, conventional optical detector, is not sensible to electrical fields. It's measuring intensity, and intensity is the square of a field. So suppose we have our cantilever and it's illuminated by some lights, and basically all the light is coming back to the detector, and it of course includes near field component and the background component, whatever is going, which is not near field related. So if we multiply it to square, we would see that, okay, we have a pure background component, a pure near field component, but there's also one component which is mixing the near field with the background, which is called basically multiplicative background, and it's not that easy to avoid it. Yeah, it's very often that it's overlooked. This is really important. It turns out that yes, it is quite important, and none of these methods is basically doing anything with suppressing the multiplicative backgrounds. So what can we do to suppress it? Essentially, we can introduce some additional modulation into our system, which could be done by the reference mirror, and then we would get the sidebands. So now in our new system, we would have 3 different field components. One is coming from a tip, which is near field. The second one is a background, which is coming from a tip again. And then we have a modulation of reference field as well. And if we do the math, we would realize that there's one term which is not depending on background by any means. And we can create our sensing method in a way that we can be sensitive only to this specific component, and we can just ignore all the other ones. What it gives us basically is a complete background suppression, and the only thing which we're extracting is pure near field related information, which is both amplitude and phase result. So next, the detection type of this SNOM is called heterodyne detection, because essentially you're adding one more frequency and you're mixing them together in the system. This configuration is getting near field amplitude, near field phase, and also there is a multiplicative background suppression. And that's the technology which we're basically using, or which was implemented more or less by the founders of the company. Here's the example of DGQ lattice. If somebody knows this is basically silicon dioxide squares located on the surface of silicon substrate. And if the background is not suppressed, we see a blurry image of something, although we can distinguish some squares or some objects at nanoscale more or less. But clearly the image to the left is much more pronounced, and we even can see or can distinguish between the ultra thin layer of silicon dioxide, which is 105 nanometers roughly, and the bare silicon substrate. So let's move on to more details, how the techniques are looking in our system. Basically, we have two technologies which are using scattering SNOM. One technology is called imaging setup, or it is basically using the heterodyne detection or pseudo-heterodyne detection as we're using it here. And that basically works for highlighting some specific material. So suppose you have our system, which I described earlier, and we have a single frequency laser. What we can do is that we can tune our frequency or our energy of laser to some specific energetic line, spectral line, which will correspond to the absorption of the material. And then basically we can only profile this specific absorption line on our surface to get the 2D images of the material which we're looking. And out of this setup, we can get two channels. One channel is amplitude, the second one is the phase, and it is considered that the reflectivity or amplitude channels corresponding to local nanoscale optical reflectivity, and the phase is corresponding to absorption for normal materials. So let's move on to the next setup, which is called nano-FTIR, which is basically the name how we are known to people. Nano-FTIR is using not a single frequency source, but instead it's using a broadband source. And the idea is that we kind of using the same idea as is used in conventional FTIR systems, where we moving our reference mirror, and then we can create an interferogram, and then going through a Fourier transform, we can extract basically spectra of the material. So if we're measuring some point and we're moving our reference mirror, we can get, again, reflectivity and absorption spectra of that particular point at nanoscale. To show you some examples, the technique is working. Basically, there's a paper in ACS Photonics, which is demonstrating the resolution of the method. Here they've created a super sharp metal AFM team specifically for this experiment, which is basically the apex is 5 nanometers, which is not typical for cantilevers, but it's possible to do so. And then they profiled the material, the interface going across the interface of the material. And then we can see that on height, on the left top image, we see no variation because the metal in dielectric is covered somehow underneath the surface. Whereas if we're checking the near-field optical signal, we see a change in permittivity, more or less. And this basically proves the resolution, nanoscale resolution of the method. The second picture is comparing far-field and near-field spectra, which are received from a conventional FTIR system and the nano-FTIR from our device. And we see a good correspondence between central frequency, the magnitude of the peaks, and the line shapes of the spectrum. So with that, I'm gonna finish the technical part describing how the device is working and move forward to some examples which were created by our users or ourselves in our nanofactory as research. Is anyone,
Short question. So as far as I understood, you're both moving the mirror and also keeping the oscillation on, right? So you,
yes.
So you use
the tip is oscillating at roughly 300K kilohertz. and the mirror is translated in a nano-FTIR within seconds range, more or less. And on the previous setup, it's not translated. Instead, it's modulating because we're mixing some additional frequency into our setup. So it's creating some low frequency, and thus it's creating some sidebands. And these sidebands only correspond to near field. So this is a near field imaging.
The question was if you are moving the mirror, it should also be oscillating to remove the background.
No, for nano-FTIR it should not, because all the background it is background, it is visible. As a moving mirror, the only thing which we're changing basically is the near field, and all the background is stable there. That's the same in a conventional FTIR system. This is basically. So
nano-FTIR is not a heterodyne scheme.
No, it's not a heterodyne. Instead, you're removing the background inclusions because it's visible there, because you're translating the mirror and you see that the constant part there is basically the far field. So you shouldn't go to tricky schemes here. You can just remove the part which is not changing. Yes?
So you are not scanning with your sample during this measurement?
I do.
So you still scan. So how much does it take to acquire a spectrum from a single point? Of course, it depends on the resolution.
3.3 milliseconds.
3.3 milliseconds for which resolution? It depends on the number of points you have.
No, per point.
1.3 milliseconds.
One measurement point is.
And how many positions of the mirror do you have for that?
Okay, and then for each point you have at minimum 3.3 milliseconds. Yeah, and if you're going, for instance, for I don't know 200 or 300 pixels positions of the reference mirror, then you just multiply it and get your result.
So the maximum number of points is
10,000 maybe. I don't know. It makes no sense to go too much, because in the end, the resolution which you're getting in wave numbers is restricted by the length of the interferometer arm. And then if you're putting too many pixels, it doesn't matter, because the resolution is not changing anymore.
okay.
It's not becoming better. But basically, yeah, if you want to get decent spectra, it takes, I don't know, 2 seconds, 3 seconds, yeah, on average, yeah, typical scan, spectral scan.
Okay. Thank you.
I have a question also.
Yeah.
So since you use an interferometer, so some vibrations in the interferometer might start to matter when you go to shorter wavelengths.
Exactly.
So how short on the wavelengths can you go, because you don't have any like active stabilization?
Yeah, good question. So basically, we're putting our instrument into optical breadboards with some suppression, gas suppression, or active fiber isolation. But anyway, the question is really valid. What we need to consider here is that we're working in IR range, and in IR range, we can compare the micrometer scales with nanometer noise, and it won't make any sense, more or less. So until the practice is saying that until we're going really to, I don't know, 500 nanometers wavelengths, there's no problem at all with noise or oscillations or whatsoever. Yeah. Shall I move forward to the applications? Okay, cool. Then, yeah, as I said, I'm going to talk about some works which were done by our users or ourselves. There's a few topics. There's much more, but I decided, okay, just to put some illustrations, what can be achieved with this system, just that you know what's done with this system, more or less. So this is a polymer monolayer, which is about 11 nanometers of thickness, and we're using this heterodyne detection or nano imaging to highlight basically the distribution of this polymer on the surface. So we have topography on the left top corner, we have AFM phase on the left bottom corner, which is basically highlighting us some mechanical aspects of the matter. So here we just have height distribution, and in phase we have tiny aspects of what's located on the surface. And then we have two images from optics. One is related to absorption, the second one is related to reflectivity. We can see if we go down for digital zoom, the resolution is quite good. Yeah, here's 500 nanometers, and we can see the second monolayer on the top of the first monolayer, which is giving more signal. And we can even compare our spectra, which was done in black by Farfield, with the one which is done by our system in blue, and we can see that the spectra is more or less the same. And we can see also that the substrate is exactly the same for the monolayer measurements and for itself. So the next sample is, sure, sorry.
Sorry, I didn't get, how do you measure absorption?
Yeah.
Compared to reflective?
So as I mentioned previously, we're getting two channels from the system. One is near-field amplitude. The second one is near-field phase. And it is believed, or not believed, it was calculated that for 99.9% of samples, if the sample is not a highly polarizable crystal, or it's not a metal with some plasmonic properties, essentially what you're getting from phase is the absorption itself. And what you're getting from near-field amplitude is reflectivity properties. So whenever you get more near-field amplitude, that means your sample is reflecting more. Whenever you're getting higher shift of a phase, of a near-field phase, that means that your sample is absorbing the wavelength. So going next to the tire production company, there was a project that the tire production company asked us to make some measurements, and we helped them. Basically, the conventional tire industry is not thinking much about how we're doing the products. What we're doing is we're mixing 5,000 different recipes, different ingredients, and the major ingredients are basically styrene, butadiene, rubber, silicon dioxide, and natural rubber, and some other additives. But they don't really do the calculations, or we try to do, but it's not probably that successful. So in the end, we just create many examples of the tire material, and then we test it for mechanical properties and whatsoever. So we were wondering, okay, since we're mixing these three components in our product, what exactly is happening inside? Is there some aggregations of some particular material somewhere, or is one material degrading and it's not present anymore, or what's happening? From AFM topography, we cannot distinguish this information. It's just something. Yeah. What we can do, we can take different spectra for these individual different materials, and then we can see, okay, let's find the peak which is visible on one material and it's not present on the other two spectra. And then we can tune our system for piece head imaging to only highlight the material which is absorbing this particular range. And then we can create the image showing one material distribution and do the same for the second and the third one. And in the end, we can get the full picture corresponding to distribution of all materials in our tire. So afterwards, we can use some statistics and calculate some properties like area of coverage of one particular material. Then we can also measure particle to particle distance, or actually we can measure also the particle diameter itself. And that's something which is useful for what we're doing. Next, gonna talk about some life science bio applications. I think we're quite good in them, and they are also quite interesting in my opinion. This was a project done with Professor Luca Quaroni from Jagiellonian University in Krakow. Here we demonstrate the monolayer sensitivity again. And also, what is also visible here, yeah, we have three measurements from different parts. Yeah, this is a substrate. We have phospholipids on the top, monolayers, and then we have one phospholipid here, one on the left side, and then the measurements in between, which is corresponding to single monolayer and double monolayer. And if we go for spectral measurements, we would see that actually the difference in magnitudes of these peaks is actually proportional. So we're sensitive even on a quantitative level that if we have double thickness, we double our near field signal basically. Next, nano-FTIR was used to get the spectrum from single biomolecular or macromolecular. The molecule is called ferritin. It's roughly 12 nanometers in diameter. And the researchers in Nanagun University 10 years ago, roughly already, created a map where they was able to distinguish single individual macromoleculars. And here's the dust. And we're not seeing it here because it's not corresponding to the spectral response. Going next to research of Alzheimer's disease. This was actually quite a good example because if we're using Raman cannot distinguish amide bands, and that's why it was not possible to use Raman technology to distinguish or to find a solution for this disease. So what we have here is basically a microtumor cut from a brain of a person who was touched by the Alzheimer's disease. Don't pay attention to these crystals. These are just they are coming from buffer solution basically. So it's nothing related to neuron. The neuron itself is this structure. So we're getting our images on 1660 wave numbers in optics and phase. Why are we using such a wavelength? You can ask. Basically, most of the biocomponents are described as amyloids, as we have amide bands, 1, 2, 3, amide E as well. There's a lot of them. But what it means really that you have proteins, and these proteins have their own oscillation levels. So essentially, we can distinguish between secondary structures of a protein. So one protein can be chemically identical to the other one, but the way how they formed could be different. So for instance, here, this protein can form alpha structure, which is helix. Basically, the protein is creating helix. And then the secondary structure of a protein can be a sheet, which is called beta sheet. And depending on this secondary structure, the protein is behaving differently. And in order to distinguish that, we can deconvolute the amide peak basically and see, okay, we have here the beta sheet peaks, and here we have alpha helix peaks. And we're doing measurements on 1660 to get the alpha helix distribution, which is a healthy state of the protein in the body. And then we can concentrate on beta sheets, which is 1636 wave numbers. And here we can see the aggregation of this beta material inside of neuron. Here, for instance, here, again, you shouldn't pay attention to buffer because it's changing the result. But what is really good is that we can see these bright spots inside of a neuron, which is confirming that you have the aggregation of the beta protein inside. And the beta protein is basically the source for Alzheimer's disease. The brain stops working and it's not functional anymore as soon as you have these beta proteins instead of alpha helixes. Going next to probably the topic which is desired most by people who are sitting here today. I'm going to talk a little bit about metamaterials, plasmonics, and Polaritonics. This is the visualization of polariton, which is propagating on the surface of graphene. It turned out that graphene is a 2D material which is really squeezing the light. And if we can launch a polariton with the tip, it propagates along the surface, and the wavelength of it is basically 40 times less when it's going in the vacuum, in the free air. So this is quite a good knowledge because the field is really squeezed again, and thus we can create some nano devices because we have a really good enhancement of the field from it. Here's some other slides where the people tuned the frequency of oscillation basically between 9 and 10 microns. I have to add one thing. Yeah, what we're seeing here is not the polariton imaging itself. What we're seeing here is the interference image between the wave which was launched by the tip, reached the end of the flake of the graphene, and then moved back. So basically, the period of this pattern is different in twice compared to real period of a polariton. So here we played a little bit again with frequencies, and we created the patterns of different standing waves across this graphene. I'm going to move a little bit faster because I think I'm limited in time. Here's another example of metamaterial, This is hexagonal boron nitride, or metamaterial formed from hexagonal boron nitride. Basically, we just put the stripes of hexagonal boron nitride. The good property of this metamaterial is that it is hyperbolic metamaterial, which is having a hyperbolic function. There are two options what we can do here. We can launch the waves with the tip, as was done in previous example, but also we can just eliminate the nano antenna located on the surface and create a wave inside the material, and then we can basically profile only the polariton with the tip. So the tip is not creating the polaritons itself, but it's collecting the waves. So yeah, the dispersion of material is hyperbolic. Another good example, I really liked it because we're working here in a terahertz range, and there are not so many sources, or for sources it's more or less fine, but there's not so many detectors which are working in terahertz. And the people were wondering if we can get the same wave of polariton propagating at terahertz ranges. So what we did here is basically, you cannot use optical detector, but you can use some other mechanisms to profile it. Here, we launched the polariton with terahertz across graphene, or we believed to launch it. We didn't know by that. But also we created a split gate underneath of the graphene, which was where we applied the bias potential, basically. And then, if you put a tip on this gap, and then you get the enhancement from a polariton, because polariton is basically the oscillations of the electric field, more or less. And in the point where you have enhancement of a field, of course, you would have more coupling, more interchange between graphene and the tip. So basically, in the points where they got the tip, they got bigger photocurrents happening, which they were able to record. And in the points where the intensity was not that big, where photocurrent was less. So this is how we created basically the dispersion map in the terahertz range for graphene plasmonics of Polaritonics. One example from Twistronics, yeah. People here created a small angle of, I think, 0.06 degrees between two graphene monolayers. And by applying different gating voltage on the substrate of this graphene, we've created a different more or less superlattices created by interference patterns of surface plasmonic polaritons on twisted bilayer graphene. Some results from carbon nanotubes. On the right slide, researchers were able to profile the Littinger liquid plasmons, 1D plasmons. On the left slide, the researchers were able to identify metallic carbon nanotube and the semiconducting nanotube. One example from Plasmonics, there was a structure of golden rings allocated on the surface of calcium fluoride. Calcium fluoride is really flat in optics, in optical response for ranges. That's why it's really used quite often, because it's not violating anything or giving any spectral signature. So the people basically illuminated the structure from the bottom and created some phonon resonance inside these nanostructures. And then they calculated also how it's going to look like in theory. And you can see the results on the right, which are in very good correspondence. So the red-yellow images are basically field enhancements or amplitude signal. And then the red-blue images is basically phase. It says like in which direction the electrical field is directed, which is different on different sides of these particles. Yes?
Is it still an interferometric scheme here, or is just a homogeneous scheme?
No, interferometric. Otherwise, we cannot.
You're also able to excite the sample from the bottom.
Yes. Applying the polarization, which is in plane of a sample.
Yeah, so in this case, so usually you may say that to some extent you are detecting the normal electric field. So what do you detect in this case?
So in this case, here's what you get as electric field, and here's some information which says where this electric field is directed. And basically, you can even put some filters distinguishing between Z components, X and Y components. So here we're saying that there is electron density oscillating inside of these goals. We see the gap enhancement here between two nanoparticles, let's call them like this. And then we can say, okay, the charge is basically bouncing from top to down. And here it basically synchronized going from down to top. So the charges are basically, the electrons are oscillating with a phase difference of 180 degrees.
Yeah, okay, but still you need quite a few degrees of freedom to distinguish the normal and in-plane components of the electric field with those phases. So it's fixed quantities. How do you detect them? Or what kind of?
You can put filters, yeah.
Or what kind of filters you need?
Yeah, to distinguish between different orientations.
Okay.
So, I'm sorry, is this detected like in back reflection from the bottom?
It's actually transmission, but it could be done the way you're talking about. So the scheme we used here most probably was that we were illuminating with a parabolic mirror from the bottom through a transparent substrate, creating this plasmon, localized surface plasmons in the structures. And then we were profiling this pattern with the tip on the top, saying like, okay, we have a more aggregation of electrons here, comparing to, I don't know, in the middle point or whatever.
But the lecture showed that you detect in depolarized light.
Sorry?
In the left, lower left corner, you show that the detector, so the detected signal is vertically polarized. Yeah, that's fine.
Yes, it's not polar, it's an analyzer, I guess.
Yeah, it's an analyzer. So in this case, you just detect the normal.
You excite from here, yeah, incoming excitation, and then you detect it from a tip, and this is signal is collected on the top with a parabolic mirror, and then you insert some analyzers, whereas you can control the polarization which you want to investigate on the surface. Okay, moving on. I probably wouldn't comment too much on this research, but it has a really fancy images. So this is a structure which we use in the same configuration. We illuminated the sample from the bottom. We created this pattern to couple the far field to plasmon excitation on the surface. And then we analyzed basically the interference patterns or plasmonic lattice of electrical field which is happening on the surface. And then again, you have a simulation and the experiments, and in different conditions, they change some properties, and these interference patterns also changed a bit. So this is just the overview of publications. We have over 50 publications for flatland optics, so 2D materials, van der Waals materials, whatsoever. I think now it's even more, but yeah, in terms of getting the results from Plasmonics, this is a really good tool. Some other applications, or I can miss it depending on how our time is.
I think you have 5 to 7.
5 to 7 minutes, okay. I can probably go briefly for applications. One of the very first examples back to 2009 was regarding stress in the material. So you have a material, a silicon carbide crystal, which was indentated with different lots. And then you can apply the frequency, which is corresponding to lattice energy in a material. And then we can profile the stress distribution in the material. And it happened that at some point, we pushed that hard that we actually cracked the sample, and it's not visible in AFM by any means because you cannot distinguish it, but in optics we can see that stress is disappearing. One example, this is called an organic semiconductor, or pentasene, which was a candidate for photovoltaics. Basically, you have one peak briefly corresponding to this pentasene at 908 wave numbers, but there are some phase differences, like actually the sample can have two different variations corresponding to BP and TFP orientations, and the difference between them is really small. It's about 3 wave numbers. So by tuning our system to each particular frequencies here, we were able to distinguish these transitions in one particular material. One example is coming from gas filtration polymer membranes or metal organic frameworks, where they capture some dust or whatsoever. We were able to profile the distribution of these MOF, metal organic frameworks, on the surface of sample. If we're going tuning the system to out of a response of MOF, we see nothing, and then here we can see the distribution of it, which was really important to analyze the efficiency of this gas filter. Also, what we can do is we can predict the density, free carrier density in materials. So here's the nano-IR, which was doped differently, and we got the image, and here we see the middle part is illuminating more. We can also apply some theory, and we can calculate from theory that based on the plasmon resonance in this particular material, we can basically assume what kind of what is the density of free carrier inside of it, and then we can plot this information, saying like, okay, in the scales of 1 micron, we actually have a difference of this density. A little short about what we also can do here. We can do pump probe measurements. Pump probe measurements is essentially when you illuminate the sample with several pulses. One pulse is modifying material somehow, for instance, putting the electrons from band region to conducting region. The second pulse is a low energy pulse, which is mid-infrared, and this pulse can basically profile the spectral response of material without any modifications. So here we have a structure which is a graphene layer or a few layers on the top of each hour, single layer, bilayer, and tri-layer. At moment 0, we illuminate the sample with near-infrared pulse, thus putting a lot of electrons or charge carriers on the conducting zone, and it is visible here that the sample is becoming bright because it reflects a lot, because we have electrons which are free. And after 200 femtoseconds, we see that the image is becoming more darker because we got the charges are coming back to their normal state, and after 400 seconds, it's even less. So basically, by varying the difference between pulses, you can see this evolution of what's happening with charge carriers here. And after 5 picoseconds, it's going back to normal state. So it shows that we have special optical resolution, and we can also be sensitive to ultra-fast things down to 10 femtoseconds of temporal resolution.
I have a technical question.
Yeah.
What light sources do you use in the system?
Near-infrared laser.
I mean,
anything.
I'm mostly curious about mid-infrared. Is it some frequency generation? I mean, it must be like some huge laser.
Most probably, I'm not exactly sure, because like we are proposing one particular solution, which is, but the people are using different solutions. It could be synchrotron illumination. It could be, I don't know, some glow bar or
Okay, so
something.
you just provide
Yes, yeah, which is compatible with. It's possible to do such experiments on it. In our example on black phosphorus heterostructure, which is also metamaterial. So if you create such a heterostructure, black phosphorus is a material which typically absorbs a lot of light in all the spectral ranges, which is why it's probably called black. However, if we illuminate it with Near-IR pump, we can also put some, excite some electrons to conducting band. And then what we see here is that for a really small amount of time, we can actually create plasmons propagating on the top of these black phosphorus heterostructure. But after 5 picoseconds, it all dissipates and goes back to normal state. Very quickly, we have modification of our system, which is called Cryogenic. It goes from 8 Kelvin to 300 Kelvin, and it allows you to basically do some experiments in vacuum and in ultra cold conditions. We have a heterostructure with graphene and HBN, encapsulated graphene with HBN flakes. And we have sample with golden islands on the surface. And then we can profile the distributions of plasmons on the surface of a sample. And depending on the temperature, we can see that the propagation length is kind of different. It also changes the gating voltage.
Is it helium-free or does it require
Vacuum. Yes, this is a closed site liquid helium system, yes.
So it's based on Attocube or
Yeah, this was a collaboration with Attocube in the very beginning. That was the reason why our companies united afterwards, because we have a lot of things in common. So I'm coming to conclusion right in time, more or less. In my presentation, I hope I was able to show that the s-SNOM is breaking diffraction-limited optics, bringing the technology which is waveform dependent and gives you about 10, 20, or even 5 nanometers of spatial optical resolution, independent from basically the ranges, spectral ranges. Could be from visible to terahertz. We have some tricky things, patented design, which is providing full background suppression. We mostly using 2 different approaches. Well, here I cover 2 approaches, but there's more, but this is out of scope of this presentation. Basically, we have single wave number imaging and nano-FTIR spectroscopy, which is getting spectra. We can also use hyperspectral imaging to calculate the spectra per each point of 2D mapping. And I showed a few examples how this technology can be implemented. These are our users. We have more than 200 systems. There's a mistake here. Installed worldwide. Also 2 systems in Russia, in MIPT in Moscow, and in Institute of Chemical Problems, Russian Academy of Science in Chernobylovka. We're tracking the publications of our users. It's constantly raising. We're helping them with the research. So basically, this is a combined work from our side and from their side simultaneously. And with that, I would like to thank everybody for attending this seminar. And yeah, if you have questions, go ahead.
Artem, thank you very much for the very nice talk.
Okay.
Being hybrid regime. So, colleagues, do we have any questions?
Maybe I have one. So regarding the span probe setup, I guess there should be some particular
delay stage
ratio between the repetition rates of the laser. I mean, should it be much more than the oscillation rate of the probe, or what are the requirements?
Yes, you're right. The typical frequencies which we're using for pump probe is in a megahertz range, I believe, and what we're using for deep oscillation is in kilohertz range. So basically, it's like 100 times difference between them. Okay. And basically, we're synchronizing the process that they're coming at 0.0 time altogether, and then we're using the delay stage, some mechanisms to postpone one pulse compared to the other one.
I mean, so the repetition rate should be around
much
megahertz.
Yeah. All right.
And regarding the regarding the detected signal, so to what extent do you detect normal electric field or in-plane electric field, or you detect something more complicated and more complicated structure?
Yes, if you have analyzer, if you just detect the bright light, then you basically
separate.
Yeah, for people, right, it's okay for me regarding the in-plane. So in that case, you explain it with a couple of dipoles and stuff.
Yeah, you can actually do the other way around. You can illuminate from the top and then collect from the bottom, and then you can be sure that this is in-plane polarization.
But okay, but why not magnetic field? I don't know. Different near-field microscopes detect different field components. And so, as I discussed, for example, as you said, it's not completely true that it's just exactly the electric field or its component.
I would leave this for interpretation of Vali Volkov because he's a good scientist.
Okay, so to a good extent, it's the electric field component.
So to make it clear, what we're providing here is an instrumentation and some know-how how to use near-field optics, but it's too broad for us to be experts in all the applications. So we really leave the interpretation of results to the customers. And if they're publishing in the high impact journals, yeah, I mean, how can you argue about this? Well, you could.
Can you, do you know what's the noise vibration limit on this low temperature system? How good is it?
It is good. I wouldn't say, no, I don't really have numbers in my mind, like signal to noise ratio, whatever, but it's good. We've developed the system for the last 5 years. I think it's installed in Geneva, in Basov's group in New York. We've sold already quite some systems, and we're constantly developing it also with microscope. So there are some problems with thermal drifting for interferometer, but not really problem with mechanical noise, I would say. And
do you also have interferometer inside?
of course. Yeah, not the. I'm not sure. I think the interferometer. I wouldn't answer this question now, but I can get it afterwards if it's interesting.
Maybe a very short technical question about this cryo system as well. So, is it kind of based on the one of the Attocubes, or it's completely?
So yeah, you can see it here. This is our normal system which we're using, which is called Near-SNOM, and then this is the cryo module, which is having a cold finger, I believe.
Yeah. So
coming.
I mean, do you like install it on one of the dry systems?
Yeah, yeah.
Or
yes, I think so.
it's kind of upgradable. I mean, if you have dry, there is a possibility. So.
Yes, but not the other way around. If you have a Near-SNOM, which is room temperature, it's not upgradable to cryo. There's so many. The thing which I talked about with this is the nano-FTIR module, which is doing the spectral measurements, and this is nano-imaging module, which is using PS head imaging. Yeah, and here these modules are separated. The reason is why in our system, half of the price is basically the laser cost, and we are not producing lasers. We have to buy it, and laser technology is constantly evolving. So we decided, because if people want to do simultaneously both, they would have to buy 2 lasers, and that's too expensive for them normally. So we're trying to create the configuration of a system suitable for particular people and their applications. Like if they need spectroscopy, they can get one part. If they need imaging, they can get the other part. Actually, this is not true already, because there are now some developments that we can do with. But what I was talking about is that in cryo, we combined it in one particular part. So basically the stage, the translational FTIR station in cryo is as well working for PS head. So we can use just one module instead of 2. It's quite a different system. But if you have up to dry cryostat, yes, I think most probably it will be compatible to cryo-SNOM.
So, okay then, thanks to everyone for coming and joining us online. Artem, thank you very much.
My pleasure. Thank you.